We're going to switch gears for the rest of this module and get a little more theoretical. We're going to talk about 3 ways IPv4 and IPv6 can coexist and even interoperate with each other in the same network. The first is what's called a dual stack configuration. Dual stack simply means a host or any network device runs both IPv4 and IPv6 simultaneously. This is actually what our Cisco routers are doing, running both IPv4 and IPv6. Now, the big caveat to dual stack is that if host A needs to communicate with host B using IPv6, the entire network path must support IPv6. And in a large network, that can be a problem. So to get around this, we have another method. Tunneling. Tunneling allows some devices on a network to use IPv6 without having to have IPv6 enabled on every device in the network path. Suppose we have 2 dual stack hosts connected by 3 routers, R1, R2, and R3. R1 and R3 support IPv6, R2 does not. Well, if host A and host B want to communicate using IPv6, they need a way to somehow get those IPv6 packets sent over these 2 IPv4 segments. And the way that's done is by encapsulating or tunneling the IPv6 packets inside of IPv4. R1 breaks those IPv6 packets up and shoves them into an IPv4 payload and sends them through R2 to R3, and R3 reassembles those IPv4 packets into IPv6 packets and sends them to host B. Pretty cool. By the way, in order for this to work, both hosts must be running IPv6. Tunneling is not translation. In other words, tunneling does not allow an IPv4 only host to communicate with an IPv6 only host. In order to do that, we need the next method, translation, specifically Network Address Translation 64 or NAT64. NAT64 translates between IPv4 and IPv6 hosts, and there are 2 major types, stateful and stateless. Here's how stateful NAT64 works. Host B is IPv6 with the address 2001:2, and host A is IPv4 with the address 10.1.1.1. R1 is configured to perform stateful NAT64. Host B sends an IPv6 packet to 10.1.1.1 by appending the IPv4 address to the end of a special IPv6 address called a NAT64 prefix. Host B sends that to R1. R1 receives the IPv6 packet, decapsulates it, re-encapsulates the payload as IPv4, and sends it to host A as an IPv4 packet. The source address of the IPv4 packet belongs to R1. Now, R1 maintains a mapping of IPv4 to v6 translations. Host A can therefore reply back addressing the packet to R1, and R1 will look at its mapping table to figure out that it needs to forward the reply to host B. All this happens transparently to both hosts, and no special configuration is required on the hosts. In stateful NAT64, the router can map multiple IPv6 addresses to a single IPv4 address, much like what happens in port address translation. This, however, means that the IPv6 host must initiate traffic to the IPv4 host. The IPv6 host must go first in order to create that translation. Now, NAT64 can also be done in a stateless configuration. Instead of the router having to perform a dynamic mapping, the IPv6 host address has an IPv4 address embedded inside of its IPv6 address, obviously in hexadecimal format. In other words, the translation from IPv4 to IPv6 occurs by virtue of the IPv4 address being embedded in the IPv6 address. There is a one-to-one mapping between IPv4 and IPv6. All the router has to do is look at the address to figure out how to translate the packet.